Now we're both feet into quantum mechanics, and we definitely are going to need this section. All right, so this one you want to take good notes on, and yeah, you'll need it. All right, so understanding quantum theory or quantum mechanics in terms of electrons and atoms, right? Because electrons are really what chemistry is all about. The movement of electrons, the sharing of electrons, the trading of electrons. This is chemistry. This is what it's all about. So we're going to gain incredible predictive power from this section alone. All right. So first of all, electrons and atoms can exist only in discrete energy levels, not in between them. We've established that already. In other words, the energy of an electron in an atom is quantized. That means it can only be this or that or the other thing, but not anything in between. Okay. The energy can be equal only to specific values, which we've said before, and they can jump from one energy level to another, but cannot exist in between these energy levels. All right, so first of all, the principal quantum number, the energy levels are labeled with an n value where n is equal to 1, 2, 3, or so on. Okay, this is called the principal quantum number. Generally speaking, the energy of an electron is greater for larger values of n. So if you have an electron where n is equal to 1, it's going to be less energy than for an electron where n is equal to 2, right? So generally speaking, the energy of an electron is greater for larger values of n. This is the principal quantum number, n is. It can have values of 1, 2, 3, and so on. And the principal quantum number defines the location of the energy level and is very similar in concept to the Bohr model. Very similar. Matter of fact, that n can be considered the same. Well, we learned with the Bohr model that n in there is just like the principal quantum number, okay? So let's look at a figure from your textbook. If your nucleus is here, n is 1, your electrons are going to be roughly here, right? If n is 2, your electrons are going to be roughly here. Electrons is 3, they're going to be roughly here, right? Very roughly, okay, I admit that. You physicists who are listening. Atomic orbitals, their principal quantum number is one of 3 quantum numbers used to characterize an orbital. An orbital is a general region in an atom that an electron is most probable to reside. So you can consider an orbital to be like an orbit. It's not the same, but you can consider it to be like an orbit, or you could consider it to be like a house that a person lives in, or a town that a person lives in, right? Those are orbitals. That's where the electrons reside. All right, and they're most probable to reside. We're going to add more details to that later, but we can consider it to be there, okay? So the quantum mechanical model specifies the probability of finding an electron in a three-dimensional space about the nucleus, which we've already said. Now, the angular momentum, so I've told you about n, which is the principal quantum number. L is the angular momentum quantum number, right? Here's L. And it's an integer that defines the shape of the orbital, okay? So L takes on the values 0, starts at 0, and it goes all the way up to n minus 1, whatever n is. And so if n is 3, then L could be 0, 1, or 2, right? Because n minus 1 will be 2 here, right? So for n is equal to 1, L can only be 0 because n minus 1 is that, right? So the third energy level will have a couple different L's. The first energy level will only have one L. All right. Orbitals with the same value of L form a subshell. Orbitals with the same value, I should say really of N and L, form a subshell. Okay? So we oftentimes use letters instead of the numbers. The numbers we'll use for calculations. The letters we'll use when we're talking about them. For L is equal to 0, we're talking about an s orbital. For L is equal to 1, we're talking about a p orbital. For L is equal to 2, we're talking about a d. 3 is f, okay? And that is all we care about. So the s subshell has a spherical shape. I'm going to show you a picture in a second. The p subshell has a dumbbell shape, and the d and f orbitals are pretty complicated, okay? So we're definitely going to be asked to recognize s orbitals are going to look like balls, and p subshells, depending on who draws them, they're going to look like dumbbells. Okay, so here's some pictures of these. S's, look at that, there's a sphere, can you see that? And here are P's. Sometimes people draw a P. Look at, I'm going to redraw that, okay? Right, I'm going to redraw this one here, over here, okay? So sometimes people will draw that as a dumbbell, right, like balloons. So if you Google this, you're going to find lots of good resources online. But different people draw them different ways. And so it looks like your author of your textbook here draws it like this for a reason, by the way. It's not arbitrary, okay? So, but anyways, draw it like that. This is also the same thing. These two pictures are the same thing. So watch out for that. You're going to see different representations. So you can see you've got a dumbbell on the x-axis here, a dumbbell on the y-axis is here. There's the dumbbell on the y-axis, and here's the dumbbell in the z-axis. Can you see that? Now D's are complicated. They're just there. You know, you've got like a toroid, like a ball with a dumbbell through it, and the rest of them don't look like that. F orbitals, you've got like two toroids here, right? There's two donuts with a dumbbell through it. There's lots of weird stuff going on here, okay? Amazing, absolute amazing stuff. The S's and the P's are the ones I'm going to ask you to recognize. Okay, so the third quantum number, we talked about N, that's the principal quantum number. We talked about L, which is the angular momentum quantum number. Now we're going to talk about the magnetic quantum number, which is M sub L, okay? And this specifies the orientation of the orbital in space. All right, so the value of M sub L depends on the value of L. So if L is 0, and then M sub L, see, look at this, here's the rule. M sub L can only go from negative L to positive L. So if L is 0, it can only be 0. But if L is 1, it can be -1, 0, and 1. If L is 2, it can be -2, -1, 0, 1, and 2, right? All the way from -L to positive L. There are this many orbitals with the same L value. Okay, one S orbital, and so on. I think I'm going to let you just figure that out. That's not super fundamental. Let me put that there in front of you and say we're not going to be counting orbitals very often, and I think that it's few enough that we can actually just do it manually, I think. So a formula is not here going to help you. All right, so when referring to an orbital, usually both the N and the L are reported. So here's an orbital. We might say the 2s orbital or the 3p orbital, right? Can you see there's my N and there's my L, right? Where for S, remember for L is equal to 0, we're going to call that S. For L is equal to 1, we're going to call that P, right? So this is L is equal to 1. This is N is equal to 3, right? In the case of a hydrogen atom, energies of all the orbitals with the same N are the same. Okay? This is called degeneracy. And degenerate orbitals are orbitals that have the same energy. Did I say that right? Orbitals that are degenerate are orbitals that have the same energy with respect to each other. Okay? So we'll use that term again in just a moment. However, in atoms with more than one electron, this degeneracy is eliminated by electron-electron interactions. Orbitals that belong to different subshells have different energies. Orbitals that belong to different subshells have different energies. Orbitals within the same subshell are still degenerate, and they have the same energy. Okay, so here's an example. If we draw an energy diagram, which you've probably seen something like this before, we might say, all right, the 1s are going to be down here. The 2s are going to be here. 2p's are a little bit higher, right? 3s's are here. 3p's are a little higher. 3d's are a little higher yet. 4s is actually lower than 3d, right? Can you see that? So this is an energy diagram for orbitals. Can you see that these three are all in the same energy level? That means that they are degenerate. Okay, I guess there's a joke that might come from that term degenerate, but I'm not going to use it because I'm not feeling clever enough today. So now finally, the last quantum number is the spin quantum number. We talked about the principal quantum number. We talked about the angular momentum quantum number, and we talked about the magnetic quantum number. And they define the region of space where an electron is most likely to be located. They define where the electrons are. Spin is different. Spin just talks about an intrinsic rotation property of it, like it's spinning, okay? An electron can only spin in one of two quantized states, plus 1/2 or minus 1/2. All right, any electron, regardless of the atomic orbital it is located in, can only have one of these two possible spins, plus 1/2 or minus 1/2. All right, just, this is going to make like a magnetic field, or it's going to be oriented when it's exposed to a magnetic field, and it's going to spin. And there's my spin that way, or it goes this way if the north pole of the magnetic field is down. Okay, so those are the quantum numbers. You're not really going to like those until you practice with those, and that's what our homework is for. So hopefully you're all set for homework, and now we're going to go really learn it when we practice it with homework.